Welcome to Lecture 2, the second of the two introductory lectures. In this one, I want to talk about physics language, or rather, physics languages, the languages of physics, because there are two languages I want to talk about. Now, I've taught introductory physics for decades, and I've taught a lot of students. And students commonly come into physics thinking what's challenging about physics is that it's mathematical. I think often they have a lot more trouble with the verbal language, the meaning of words, the meaning of concepts, and then they also have trouble converting physics concepts into math. That is a big issue that involves both English language, or whatever language you're speaking, and math. But really, understanding the words and the concepts used in physics and understanding them precisely is really important. And one of the reasons there are problems here is because we use words slightly differently in science and in physics in particular. We may have meanings that are related to the everyday meanings, but they're more precise. Let me give you some examples. So here are some words that you've all seen these words, you've seen all these words, you know what these words mean in everyday language, and they mean something similar but not exactly the same in physics. Work and energy, two closely related concepts. Work is a very specifically defined thing. It's not quite the same as going to work, and yet it's related. Acceleration, that's one that we're going to talk about again and again and again, and I'm going to remind you over and over that acceleration means more than just speeding up. And getting that it means more than just speeding up is the key to understanding things as disparate as why a car goes around a corner without skidding off or why a satellite doesn't fall down. Energy and power, two concepts that are confused every day in the media. They're very closely related. They're different, though. Inertia. We talk about someone who has inertia because they can't get themselves going. Well, that is a good metaphor for the physics concept of inertia, which is more precise. Space and time, two really important ideas. We all have intuitive understandings of them that we developed from when we were young children. We'll find out when we get to relativity that they aren't quite what we think they are. Potential. That person has great potential. Well, potential, again, has a very specific meaning in physics. Heat. Heat is not quite what you think it is. It's got a precise meaning that is related to what you think of as heat, but isn't quite the same thing. Exponential. I'm always hearing people talking about something is happening exponentially, as if exponential just means something that happens quickly. Nope. It's got a very precise mathematical meaning, and there are many processes in physics that occur exponentially. Vector is kind of an interesting one because I teach not only physics but environmental studies, and when I'm teaching environmental studies, I'm sometimes talking about vectors as disease carriers, and the people who get most confused by that are my physics students, for whom a vector is a very specific kind of mathematical object. Collisions, we all know about collisions. Collisions in physics, again, have a very precise meaning. The last two words on here, uncertainty and theory, are words that I'm going to go into in more detail, so I'll spare you more about them until I talk further about them. Let's look at theory and uncertainty. Very frequently you'll hear someone say, that's just a theory. What do they mean by that? Well, the everyday meaning of it's just a theory is it's a guess, it's a hypothesis, might or might not be correct. It's just a theory. We don't have to take too much stock in it. And we dismiss the thing that is deemed to be just a theory. In science, theory has quite a different meaning. A theory is an overarching, coherent framework that explains and relates a whole body of scientific knowledge. It's been verified by lots of experiments and observations. It's self-consistent. There are no internal contradictions in it. And it hasn't been contradicted by any experiment or observation. If it ever is contradicted by an experiment or observation, you can be sure scientists are going to look very, very closely at that experiment, those observations. They're going to repeat them over and over and over again. And if the contradiction with the theory keeps showing up, then the theory has to go, because reality is our gold standard for what is true. And if we have a theory, and we've developed this theory on the basis of a relatively few observations and experiments, as time goes on, the theory begins to subsume more and more phenomena under its umbrella, and we have more and more verifying experiments and more verifying observations, and confidence in that theory grows over time. Let me give you some examples of theories in science. In the other sciences besides physics, which is what we're talking about here, the theory of evolution is a very, very firmly established theory in biology. Doesn't mean that we know every single step in the process of every single species evolution, but we do know the big picture, and we're confident that that big picture explains the origin of the species we see on Earth today. Plate tectonics, a relative newcomer to the scientific theories, really only became firmly established in the second half of the 20th century. Plate tectonics is the theory that the continents move about. It explains a host of things about planet Earth that before seemed to be disparate ideas that didn't have anything in common. Physics, the theory of relativity. I put that one in because it's the one that's got the name theory. It's not just a guess or idea. It's a firmly established basis of our understanding of physical reality. Quantum electrodynamics, a name you may not have heard of. Richard Feynman is a name you may have heard of, and he's one of the originators of quantum electrodynamics, QED, is really one of our most precisely verified theories of physical reality. It's actually a combination of the theory of relativity and Maxwell's electromagnetic theory, two other big theories that are pillars of physics. Newton's theory of gravity is another theory we often see referred to, especially when someone disparages the idea of theory. Then you say, well, what about gravity? I put Newton's theory in quotes because Newton's theory has been superseded by Einstein's general relativity, but Newton's theory is still very relevant in a wide range of everyday situations. So there are some examples of theories in science. Theory was one of those words. The other word is uncertainty. So let's take a look at uncertainty. The public has a very hard time with uncertainty. And so scientists have a hard time communicating to the public sometimes because we don't want to say we're certain of anything. I've actually been a witness in a court case where I was asked as a scientific expert to quantify something. And I said, well, I know this to within this many meters or that many meters. Was the pedestrian in the crosswalk or weren't they? Well, I give you this statistical distribution and I am 95% confident. And the lawyer says, well, you don't know anything. Well, nobody in science ever knows anything precisely, and neither does anybody in any other area of human knowledge. We have uncertainty in science. And there are really three reasons for the uncertainty. But basically, it's that nothing is 100% certain. Theories themselves, we think they're right. They might not be. Scientific revolutions that actually overthrow theories are rare. More common is kind of a gradual evolution in our knowledge and refining the ideas until we get more and close to an accurate description of physical reality. So we're converging on a true and accurate description as our theories evolve slightly. But once in a while, there is a true revolution that overthrows established theories. Then there's uncertainty in numbers. And numerical uncertainty takes several forms. It's the uncertainty in measurements. Our measuring instruments are simply not perfect, and so we can't get precise values of the things we measure. In projections of future events, for example, we know that global warming is occurring and we know that human beings are the predominant cause, but we can't tell exactly what the temperature is going to be 50 years from now, partly because we don't know how human beings are going to behave, but partly because there is uncertainty in our models and our projections, and our knowledge of every single physical and biological and chemical event is just not 100% certain. So there's numerical uncertainty in measurements, there's uncertainty in projections, and then as we'll see late in the course when we get to quantum physics, there is a fundamental uncertainty described by something called the Heisenberg uncertainty principle, which makes uncertainty one of the fundamental properties of nature at the quantum scale, at the most fundamental scale. So get used to uncertainty. I won't be talking a lot about uncertainty in this course. It will be implicit sometimes in numbers I state without very many decimal places because I just don't know much more about the accuracy or precision of those numbers. But uncertainty in science is a big deal and it's important, and there is uncertainty, and we need to know how to quantify the uncertainty. But the fact that there's uncertainty does not mean in any way that science is wrong. Now, as we're talking about uncertainty in numbers, that leads me into the second great language of physics, and that's the language of mathematics. And I want to begin talking about mathematics philosophically. I want to raise a philosophical question, which I'm not going to answer. And the question is this: is math a science? Is it about reality? Or is it just some kind of human construct? And I want to give you two quotes from two very famous individuals who have thought a great deal about this question. Mathematics, is it a science or a human construct? So here's what Bertrand Russell says back in 1902. Mathematics takes us into the region of absolute necessity, to which not only the actual world, but every possible world must conform. So Bertrand Russell is seeing science, this is in his essay, The Study of Mathematics, he's seeing mathematics as something which is sort of a meta-science. It constrains not only the science of our world, but every possible world you could imagine. And if you think that's a bit fanciful, wait for lecture 60, when I'm going to introduce the idea that we may possibly live in a multiverse of different disconnected universes, each of which may have its own laws of physics. if that picture is true, and if Bertrand Russell is right, nevertheless, the rules of mathematics have to reign in each of those individual universes, even though the rules of physics may be different. Wow. So Bertrand Russell's idea is mathematics is really sort of at the foundation of physical reality, more so even than physics. On the other hand, Albert Einstein here is a little bit puzzled in 1922 in his little publication, Sidelights on Relativity. How can it be that mathematics, being, after all, a product of human thought, so he thinks it's a product of human thought, which is independent of experience, is so admirably appropriate to the objects of reality? So Einstein is wondering, he thinks we've sort of made up mathematics, and yet somehow it does such a beautiful job of describing physical reality. Well, I'm not going to answer this difficult philosophical question, but I am going to say they're both, Einstein certainly is correct, and Russell may be right. Einstein is correct in that mathematics is a beautiful language and a concise, efficient language for describing physical reality. And you'll see that again and again in this course, and sort of the elegance with which we can state important big concepts and relationships mathematically. So mathematics really does have a special place in physics. And when you think mathematics, the first thing you probably think is numbers. And though numbers are important, we're going to spend most of the rest of this lecture on numbers. But before we do, I want to say that mathematics is also much, much more than numbers. It expresses concisely profound and universal relations and interactions. And I'll give you one example of this. It's going to be pulled back from Lecture 13 a little later in this lecture to see how that goes. So don't think about mathematics as just being about numbers. On the other hand, when we're going to do mathematics and do quantitative science, we need numerical answers. We need to know how big something is. We need to know when some event will happen. We need to know how fast a spaceship has to go to get it into a circular orbit with a period of 24 hours so it will serve as a communications satellite. Or we need to know what to do to get a satellite up there to run the GPS navigation system. We need to know how fast it's going to be going. We need to answer quantitative questions. So we need to use numbers. Let's talk about numbers in physics then. First of all, they express the sizes of physical quantities, and they have to be accurate if they're going to be useful. How accurate? Well, that depends. So I could tell you that I'm in my car going 50 miles per hour plus minus 1 mile per hour because I really can't read my speedometer to better than about a mile per hour. That's a question of accuracy. I'm going 50 miles an hour, but I don't know that. I'm uncertain by about plus or minus 1 mile per hour. So that's the question of accuracy. There's a related but distinct concept of precision. How finely can I tell the number? I can tell you in one car with a digital speedometer that the speedometer reads 49.78 miles per hour. That's precise. I can distinguish whether it reads 49.78 or 49.79. That tells me I've got 4 digits of precision. What it does not tell me is how accurate that might be. That speedometer might still be off by plus or minus 1 mile per hour. So if I say it reads 49.78, it might really be somewhere between 50.78 and 48.78. And it would be kind of stupid to have a speedometer that was that precise and yet that inaccurate. I'm currently doing battle with a company from which I have a nice digital thermometer, one of these ones that has a little outdoor sensor and radios the temperature back, and it reads to 1/10 of a degree, so it will say it's 54.7 degrees out. And I said to the company, can I really believe that? They said, no, it's only accurate to plus or minus 2 degrees. Well, it makes no sense for them to give me 3 digits of precision if the thing is only accurate to 2 degrees, but that's what they chose to do because they think it looks more scientific. You want to get precision and accuracy kind of correlated. It makes no sense to be precise if you're not very accurate. So accuracy and precision are 2 important features of numbers that are expressing actual quantities in physical reality. We also need to cover a very wide range of values. And we do that with scientific notation. For example, here's a big number, 650,000,000. Got to think what it's 650 million watts. That happens to be the power output of my local nuclear power plant in Vermont, the Vermont Yankee Nuclear Power Plant, 650 million watts. But I can write that more easily as 6.5 times 10 to the 8 watts. W there is the symbol for watts. Or I can write it with so-called prefixes that tell you what multiplication to make. And so 650, 000, 650 million watts can also be written as 650 megawatts. And I will use both scientific notation and these prefixes throughout the course. We're going to be using almost exclusively, not entirely, but almost exclusively, the so-called International System of Units. I'll say more about that in a moment. And in the international system, a whole bunch of these prefixes have been defined, and most of them involve every 3 powers of 10. And you're familiar with some of them. You know kilo stands for 1,000. A kilogram is 1,000 grams. A kilometer is 1,000 meters. You probably have heard of giga, because your computer probably runs at about 3 gigahertz, 3 billion clock cycles inside the computer, 3 billion simplest things it can do every second. Giga means a billion. A gigawatt is typically the power output of a large power plant, 1 billion watts. You may or may not have heard of a terawatt. Humanity uses energy at the rate of 15 terawatts. Some of these others you haven't heard of at all, but they're used in a variety of sciences. For example, ecologists studying the global flows of carbon in the world's ecosystem will talk about quantities in petagrams, peta being 10 to the 15, so a petagram is 10 to the 15 grams. On the other hand, we go down to small things. You're familiar with milli, lowercase m, for thousandths. Micro, Greek symbol mu, for 10 to the minus 6, or millionth. Nano, we've already talked about in Lecture 1, for a billionth. And some of these are less familiar, and I will use them throughout this course. And when I use one that's either unfamiliar or that I haven't used before, I'll try to remember to say what it is. But you have this table, and you can find this table lots of other places. If you ever come across a prefix that you don't know, look it up. And you will notice something else here. Most, but not quite all, of the prefixes for quantities that are multipliers bigger than 1 are given capital letters, and quantities that represent divisions, that is, smaller than 1, typically are given lowercase letters, although there are a few exceptions. So those are the SI prefixes. Now, in physics, we're dealing with physical quantities, and most physical quantities have units. And I want to emphasize that the systems of units we use are, in fact, human artifacts. 3 of the most important physical quantities, the fundamental quantities, certainly in mechanics, are length, exemplified by this meter stick, mass, exemplified by this massive bowling ball, time, exemplified by the clock. We have units for all these. The meter happens to be the unit of length. The kilogram is the unit of mass. The second is the standard system, international system unit of time. We have a number of other units that are important, and here's a table that talks about length, time, mass, meter, second, kilogram, the ones I just mentioned. But there are other units in other systems. The foot, the yard, and the mile are measures of length. The hour, the day, and the year are measures of time. The ton, the English ton, the ton with 2 N's, the metric ton, and the slug are units of mass. The slug, not the pound, is the English unit of mass. Speed and velocity we'll measure in meters per second, but you often measure them in miles per hour or kilometers per hour or whatever. Force is measured in newtons. It's pounds in the English system. That's what a pound is a unit of. Energy in joules, power in watts, and lots of other units for energy. Calories, kilowatt hours, BTU, ergs, electron volts we use later on. Power in horsepower. Temperature, the official unit is the Kelvin. We'll sometimes talk about degrees Celsius, less often about degrees Fahrenheit, the everyday unit in the United States, and almost never about degrees Rankine. We'll look at electric current, electric potential difference, the volt, and a lot of other units. It's important when you're doing a calculation or expressing a result to have the unit there. If I tell you how far is it from your city to the next city, and you say it's 50, I have no idea what you're talking about. You've got to tell me it's 50 kilometers, 50 miles, whatever. The unit is crucial. I take off on my students' exams if the unit is not there in the answer, even if they did everything else correctly. Our standards of units, how do we determine what a meter actually is? I mean, here's a meter stick. We bought that from a company that makes wooden meter sticks. But how do they know it's right? Well, each of these units has a standard. And these standards have evolved over time. And what we're trying to evolve toward is a situation in which the standard of any one of these units is something any scientist anywhere could create or recreate in a laboratory. Now, in the old days, all the standards were specific objects. There was a prototype meter, and that defined the meter, a particular real object. There is still a prototype kilogram. It's held in a vault in Paris, very constant temperature and everything, and that defines the kilogram. And that is an unfortunate measurement because I can't go into my laboratory and determine what the kilogram is. I have to use standards that are traceable back to that standard kilogram in Paris. And the history of this particular unit I'm going to describe, the meter stick, the history of the meter is an example of how these units evolve. So the meter was first defined in 1791, and it was defined as 1/10,000,000th of the distance from the equator to the North Pole on a meridian, a line of longitude, that went through Paris. So you start at the equator, you headed toward Paris, going north, and you went all the way to the pole. You measure that distance carefully, and that distance, take 1/10,000,000th of it, that defined the meter. And by the way, the surveyors who were sent out to do that messed up a few times, and they almost got guillotined. But they gave us, ultimately, this definition of the meter. In 1889, there was a prototype meter, a bar made of special material that has very little thermal expansion. Its length doesn't change much with temperature, and nevertheless, the length of the meter was defined to be at 0 degrees Celsius, the freezing point or melting point of ice, the freezing point of water, melting point of ice. And in 1889, and for a long time since, the length of the meter was defined as the length of that particular piece of metal. So there's an example of a prototype meter. In 1960, we redefined the meter. The international community agreed it was going to be 1,650,763.73 wavelengths of light emitted by the isotope krypton-86, more on that in our nuclear physics lectures, in the 2p10 to 5d5 transition. Wow, that's an atomic transition. We'll learn about that when we talk about atoms as we describe them in quantum physics many lectures hence. But there it was. That was a definition of the meter that anyone could reproduce, because anyone could get krypton-86, put it in their laboratory, measure the wavelength of the light coming out from this transition, and away they went. Well, that wasn't good enough either. There's an example of the laser system you might use for that. In 1983, the meter was redefined, and this is the definition that stands today, and this is a really good definition. It probably won't change. The meter is the distance traveled by light in vacuum in 1/299,792,458 of a second. Now, that's an interesting definition, because what it does is it suddenly defines the speed of light. People have been measuring the speed of light more and more accurately, and the measurement finally got so accurate that we turned things around and said, instead of talking about the speed of light in terms of meters and seconds, let's talk about the meter in terms of the speed of light. And so the speed of light is now, by definition, 299,792,458 meters per second. It's nothing anyone will ever measure again. What they will measure if they attempt to measure the speed of light is how big a meter actually is, because a meter is, by definition, the distance light travels in this tiny fraction of a second. By the way, that distance is just about 1 billion feet. I know that because a convenient approximation for the speed of light is it's about 1 foot per nanosecond, 1 foot per billionth of a second. So in 1 second, it's going to go about 1 billion feet. That's another, you could think of that as a way of defining the foot if you wanted. Now, this is just one of the units, the meter. The second is similarly defined by a reproducible standard involving atomic transitions and wavelengths and timing. And that's what atomic clocks are all about. So we have a good definition of the second. We do not have a good definition of the kilogram. As I mentioned, the kilogram is still defined in terms of that international prototype kilogram. I don't think that's going to last much longer. Look for a change in the definition of the kilogram. It could come anytime. Scientists are working on making balls of silicon, perfectly spherical balls, perfectly made of silicon, and literally counting the number of atoms in those balls and scaling a definition of the kilogram based on the mass of the individual atoms. So I think we will see very soon a reproducible standard for the kilogram, and then the three fundamental units, the kilogram, the meter, and the second, will all be defined by reproducible standards that could be done anywhere in anybody's laboratory, and we won't need that international prototype kilogram sitting in a vault in Paris. So there's a history of a unit, and all the other units have equally fascinating histories. Well, a little bit more on math. We've talked about numbers, how you measure numbers, their accuracy, their precision, and so on. I've indicated that it's not just about numbers. It's also about expressions of important physical relations and their interactions, and that's what equations do for us. Equations, yes, say left side is equal to right side, and left side ultimately, when you're using the equation, has a numerical value, and that value is equal to the right-hand side if it's an equation and if it is indeed satisfied. But equations, more importantly, express fundamental and sometimes really crucial physical relations. And when a very important equation comes up in this course, I'm going to show that equation with what I call its anatomy. We're going to sort of take the equation apart and see how it works. And let me do that now for one important equation. I don't expect you to understand the equation here. This is an equation, as I said, I'm pulling it back from lecture 13. So it's an equation we'll get to in Lecture 13. It's the equation that expresses Newton's law of gravity. So the equation is called universal gravitation. Often the equation will have a picture with it to try to figure out what it means. And here in this particular case, I'm showing the Earth on the left, the Moon on the right. I'm showing the forces that each body exerts on the other with those orange arrows. By the way, I'll have a lot of conventions in this course. Orange arrows are going to stand for force. Blue arrows will stand for velocity. Different color arrows will stand for different kinds of physical quantities, and it's useful to sort of, you don't have to memorize that, but just keep it in mind and your diagrams will become clearer. And the distance between the Earth and the Moon here is this distance r. And here's the equation of universal gravitation. And the way I'm going to do the anatomy of an equation is to tell you what the individual terms mean. F is the force between two masses, m1 and m2. There are the two masses, their values in kilograms, m1 and m2. There's the square of the distance between those masses down in the denominator. This is where the English and the math come together. You can't understand that equation with just math, and you can't understand gravity thoroughly, completely, with just English. You need them both. And this is where we connect the math and the English. And finally, that's a constant, whose value, by the way, Newton did not know. It was discovered somewhat later, some decades after Newton's time. That's the constant of universal gravitation. So there's the anatomy of an equation, and look for anatomies of equations throughout this course. Okay, well, let me say a little bit more about math and what I expect from you by way of mathematics. You could go through this whole course without math, and you would still get quite a bit out of it. But you will get more out of it if you follow the math. And in cases where following the math means looking at fairly sophisticated derivations of new results, or occasionally looking at examples that illustrate a particular physical concept mathematically, we're going to use our big monitor over here, and I'm going to use it like a blackboard. And I'll often go through derivations of equations or expositions of theoretical results or numerical examples. And today I'm going to use it simply to show you my expectations for your knowledge of mathematics, which are basically high school algebra and trigonometry. If you know calculus, so much the better, but there is going to be no calculus in this particular course, although occasionally make reference to calculus ideas. But this is a course that's based on high school algebra and trigonometry. So, high school algebra. I would expect that you'd know how to solve simple equations. For example, if 2x equals 6, what's x? Take a minute and think about it. You got it. X is 3. What did you do? You divided both sides by 2. 2x divided by 2 is just x. 6 divided by 2 is 3. Simple. I expect you to be able to do the same thing symbolically. So here's an equation, ax equals b. What's x? You got it. X is b over a. What did I do? I divided both sides of the equation by a to get x alone, and b over a is the right-hand side. X is b over a. Trigonometry is about these functions, sine, cosine, and tangent, functions of angles. They're based on right triangles. We have a right triangle with some angle theta there. Theta, the Greek symbol theta, is commonly used for angles, so get used to that. Don't tune out when you see a Greek symbol. Some of my students, I think that makes harder math. That just means an angle, and that's the symbol we'll use universally for angle. So we've got a side adjacent to the angle, we've got a side opposite the angle, and we've got this hypotenuse of the right triangle, and the sine is defined as the opposite divided by the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent, or equivalently the sine over the cosine, and that's all you need to know about trigonometry. But you do need to remember that much trigonometry, and I'll ease you into it gently when we start using it. You need to know how to read graphs. What's that graph tell you? You need to know what the axes are meaning. That's time, that's distance, that's some object's motion, and you should be able to tell from looking at that graph that not only is the object moving, but its speed is increasing with time. So that's the kind of expectations I have for mathematics. Now, one last thing. Some of the lectures, not all of them, but many of them will end with a problem, a challenge problem for you to take on. These are entirely optional. You will get almost as much out of the course, 99.9% as much out of the course if you don't do the challenges. But if you like a little mathematical challenge, and they will be mathematically based problems, try them. So that's what's going to happen right now. I'm going to give you a challenge for this particular lecture. This is not going to be a very challenging challenge. Some of them will be more challenging, and I will also give you a solution after each challenge So this is actually a multi-part challenge. Solve some equations. Solve for x. 4x plus 2 equals 6x minus 8. That's a little more complicated than the equations we just did. A symbolic version of the same. A triangle. I'm telling you the angle. I'm telling you the hypotenuse. I ask you what's the height h on the right. And finally, analyzing a graph. How far has this object gone after 2 seconds? Is it speeding up or slowing down? Well, I'll let you figure those things out. Here are the answers. X equals 5 for the first one. You got it. X equals B plus D over C minus A. The triangle. The height is 10 inches times the sine of 30 degrees, and so it's 5 inches. What's the graph telling us? The graph is telling us that the object has gone about 1.4 meters after 2 seconds, and that, in fact, it's slowing down. Well, enjoy the challenges. I think you'll like them, and they'll help develop your confidence in doing mathematics applied to physics.